it's dark.
All right, well, good evening. Welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here. It's great to have a full house here, or practically a full house. I realize, again, a number of you are from Binghamton University, but we also have, I think, some families here as well. You came up on a great night for two reasons. One, to see a great presentation, but also it's one of those, I hate to say rare nights, but it's a beautiful night. It's nice and clear, and we've got a couple nice objects for you to see. If you haven't seen them already, don't worry, they'll be there when this program finishes. Again, we're very happy to be able to finally have people back up here again. Although one thing that the pandemic sort of opened up to us, if you will, we didn't realize it was opening something up for us, was the opportunity to live stream. And that's actually been a great tool for us. We've been able to actually reach a much larger audience than we've ever been able to in the past. Actually, back in December of this last year, when Jupiter and Saturn had that conjunction where the two of them were so close, they basically looked like one star, one object in the sky. We at that point had over 4,000 people on our live stream. The chat on the side looked like a CVS receipt flying by. And but we've also been able to do some live streams, live stream observing Comet Neowise last August. We also did the annular eclipse in June, and I don't know if any of you were up for that, but that actually we actually had a nice view of that as well. So it's been great to do that. It's been nice also now that we're finally open again, to actually meet some of those people that we've seen on the YouTube chat. So anyway, let's dive into this, because this is going to be a really exciting program. We're very fortunate to have as one of our educators here, Tish Bresee, who is a NASA JPL Solar System Ambassador. And with that, you get connections to other resources, like the person on the left-hand side of the screen here, Dr. Michelle Fowler. And so why don't we just pass it on to you, Tish? Let you get started.
I'm ready. Okay, were you going to try that camera?
I will.
Okay.
I just need to.
Okay, couple of basic principles we got to remember. The James Webb is only an infrared camera, which it's not meant to be putting it down or anything, but this is limited to wavelengths, okay? And there's a reason for it. So I thought maybe you'd like to see a demonstration of what an infrared camera would look like, even in the dark. Let's say we're looking for a planet in this room that might be warm. Kasha? What happened to my cameraman? He's going to get it, right? Okay. All right. So, well, let me just ask, since we're waiting for him, let me just ask, did you try that experiment in physics where you put the space telescope together and put it in the spaceship? Not too many grown-ups did that. Okay. Well, it's pretty difficult. The whole spacecraft is folded up and put into a vehicle that's going to shake and rattle and roll and take it up to 1 million miles from the Earth. So we're going to see how that works in just a moment. We were just going to wait. Here, I can do this. You want to do that first? Okay.
Well, actually, no, go ahead. What I want to do.
Getting it ready?
Gotta get it ready.
Okay.
Then,
all right. Thanks, Dr. Fowler, for your patience. Some of the infrared you can do by yourself. Your fingertips are infrared sensors. So if you stand up just for a second and feel your chair, try it. Okay, remember when you were 2 years old and you tried to touch the fire and Mom said, "Stop"? I know what that's like. Okay, now try your hair. You have warm places and cool places. So how would it show up on an infrared camera? Where are the warm places on you? Where would you take your temperature? Oh, well, except for that one. Okay.
Actually, if you give me a moment here, I'm going to shut the lights off,
All of
and
them.
I'm going to take your picture. So give me a
Okay.
second.
Right there.
Smile. Okay. It takes a moment for me to actually get it onto this computer, but we'll show that in a bit.
Okay. Is that better? Okay. All right. Before we introduce Michelle Fowler, we wanted to show you the results of this.
It's going to take me a couple minutes.
How long?
About 5 minutes.
About 5 minutes. Okay, we have time for an experiment. All right. Another heat-related experiment you can see with these. Now, I do want these back. I'll give you a couple over here. Over here. Ever get to play around with the diffraction lenses? Oh, don't take my wire. Great, grab that. One more. Until they're gone. Yes, and you're over here. All right. Then pass them back afterwards. Thank you. All right, we're going to turn the lights off again. Can you do that for me? All right. Well, put the glasses on and take a look at Dr. Michelle Fowler. Hey, Michelle.
Hello.
Okay. Well, you're not looking at her heat. You're looking at her light. Okay. And in my hand, I have a heat and a light source. This is just a candle maker. Let's see what that looks like. Can you get that quiet again? What do you see? You see a rainbow? Yeah. What are the colors? Red, orange, yellow, green, blue, indigo, violet. Yeah. All right. People that are way back there, if you want to sit up here, there's room. I promise I won't step on you. Okay. So we can see the spectrum of light pretty well through certain kind of lenses, like on the Hubble Space Telescope. The Hubble is about 500 miles up, and it's within reach to be brought back down. But the only spacecraft that I know of, Michelle will have to tell me if I'm wrong, the only one I know of that was not meant to come home, ever, is the James Webb Telescope. I want you to think about it. What does that mean?
It depends on how you define telescope, of course. I mean, we've got a lot of other stuff out there that is never designed to come back. But
well,
it's more like satellites.
Star Trek
you know,
1,
so,
you know, that one said that it's going to come back. I do.
It's not coming back, no.
Can you make it bigger? Click the plus. There you go. Hello.
So remember, we took that picture in the dark.
So where are your warm places? The light colors are warm. Dark colors are cold. If you'd like to see more detail about this, Dr. Fowler has a video, an infrared video. Just type in Michelle Fowler infrared video. You'll see it.
Yeah, it was made in 1999. You get to see me a long time ago.
It's still true, though. It's a great story.
Oh, yeah, I know. I mean, infrared light hasn't changed. Yeah. That's right.
All right. Can we get back to page 1 or no? Okay, I would just like to tell you that we got our information today, not just from Dr. Fowler, who's going to speak next, but also from Eric Smith at the Jet Propulsion Lab and the Goddard Space Flight Center. And he shared his data with me on the scope, and then we're passing it on to you, and that's my job. So we're going to ask you to think of questions along the way, and Dr. Fowler is going to have some time for questions. We have a microphone set up here, right? Oh, no, we're going to come to you. Tonight we're going to come to you. So you raise your hand if you have a question for Dr. Fowler afterwards, okay? So let's say hello to Dr. Michelle Fowler. Hi.
Hi, Ray. Hey, it's so nice to be back at Kopernik. I hope to be there in person sometime soon, but in the meantime, it's great to be here. Let me just go ahead and share my screen and make sure we get everything set up here.
Okay.
So there's my screen, and I'll start my video again. So Drew can tell me if I'm showing up. Let me start my slides. And how's that look, Drew? Can you see me? Can you see the slides?
I see the slides. I just need to get that in the right position for me to be able to show that to
the world.
The world, exactly. So give me a second. And where's the Zoom? Here's the Zoom.
Just let me know when you're ready.
Could you pass the
yes,
glasses to the center?
Yes, we are watching.
Center,
yes, we have it.
Aisle.
Okay.
We'll click them. Thank you.
Well, hey, I want to make sure everybody has a chance to go out and see this wonderful sky, so I'll do the presentation, but I also want to make sure you have time to go out. But anyway, it's wonderful to be here to talk to you about the Webb Space Telescope. My life is a mess now because of this telescope. I'm running from one rehearsal to the other. We're getting ready to launch it, as Tish said. Right now, the launch date is holding it December 18th. And we have a huge winter ahead of us. I'm not taking any time off for Christmas or New Year's or anything like that because we're going to be, well, I'll show you, we're going to be getting this telescope up and running. But let me tell you a bit about the telescope itself, a bit about some of the technology, and also some of the science that we're looking forward to doing. I'm an astronomer. I've used the Hubble Space Telescope. And I don't know if I'll ever use the Webb or not. It might be on some team, but it's just going to be an incredible thing, and hopefully we'll rewrite the textbooks about what we know about the universe. So let me talk a bit about some of the things that makes the Webb really unique and amazing. So this is a collaboration. It's multinational. It's a collaboration between NASA, the European Space Agency, and also the Canadian Space Agency. And, as people were saying, it's the largest telescope that we've ever put in place, 100 times more powerful than Hubble. So this is a follow-on to both the Hubble telescope and, as Tish mentioned, the Spitzer telescope as well, which sees an infrared light. It's so big, the mirror is so big that there's no rocket big enough to take this mirror just in its full unfolded size state. So we have to fold it up kind of like origami. And we've never done that before. We've never tried to launch a space telescope and actually unfold the mirror as we actually get out into space. So there's a lot of firsts as far as technology for this telescope. As Tish mentioned, it sees entirely in infrared light. It does not see visible light at all. And there are some really cool advantages for that. So one you guys saw just now, in the sense that anything that's warm you can actually take an image of, even if it's not emitting light. So even in a darkened room, warm things glow. And even in the darkness of space, warm things glow like dust clouds and planets around other stars. And so there's some real advantages to looking at infrared light. It's about to be launched on an Ariane 5 rocket. The only place that's launched from is French Guiana. That's one of the contributions from the Europeans, as well as being collaborators on a couple of our instruments too. And some of the things that are the major science goals. This thing will have the power to look at light so far away and so faint that we see objects as they were about 13.5 billion years ago. So if any of you are unfamiliar with this concept, light travels at 186,000 miles per second. And although that seems incredibly fast, when you think about the vast distances in the universe, it takes time for light to get to us. So the sun is about 93 million miles away. That takes approximately 8 minutes for light to get that distance. And so we see the sun in the sky as it was 8 minutes ago. Go out to the nearest galaxy, Andromeda. That light took 2 million years to get to us. And we're going to be looking so far out into space that the light actually took about 13.5 billion years to get to us. That's the time the first stars and galaxies were forming. And another one of our really major exciting science goals is that we'll actually be able to figure out what the chemistry is of the atmospheres of planets around other stars. So do the planets have water vapor or oxygen or carbon dioxide? I think that'll be a really amazingly different way to look at exoplanets, planets outside our solar system. So we, as Tish mentioned, we're not coming back. This telescope is orbiting at a Lagrange point. A Lagrange point is a balance between the Earth and the Sun's gravity. And in this case, it's a really good place to put a telescope because you don't need a lot of guidance and rockets to keep it in place. The gravity of the Earth and the Sun kind of stick it in place. And L2 is about 1 million miles away from Earth, 4 times away farther than the Moon. And to compare that, Hubble orbits about 300 miles away. So I mean that's we're going real far away for this one. And of course, that distance will also help us get to really cold temperatures, very far away from the Earth and the Moon's heat as well. So let's take a look at James Webb. So let me start here. Here's a little bit of a graphic of how big the mirror is. We compare it to Sylvia. Sylvia is about 1.75 meters. There's Hubble, and there's Webb. And so Webb is about the diameter of about a 6.5 meter telescope. And as you can see, it has segmented mirrors. These mirrors are all individually movable and focusable. And all of the mirrors are only in their right shape when it goes down to about 30 degrees below absolute zero, 30 degrees above absolute zero. So one of the things we have to do before we can actually take images with this is cool the whole telescope down and get each one of those mirror segments focused so that they all act together as one big continuous mirror. And that's one of the amazing technology changes in Webb is instead of launching a single mirror like Hubble, launching a big mirror made out of segments that can all be focused. And that's going to be a biggie. And there's that one again. Okay, so Tish mentioned that the electromagnetic spectrum has all kinds of different sorts of light. There's visible light that we're familiar with. I can use my cursor. There's visible with all of the colors we're familiar with, from violet to red. Colors really are a measurement of the energy of the light. What makes a blue photon, particle of light, different from an orange photon is energy. The more towards the blue and violet end of the spectrum you are, the rainbow, the higher energy light. And as you go down towards orange and red, things get to be lower energy. And so infrared, and the name sort of says it, infrared means beyond red. And so this is light that's too red for our eyes to see. And as you move farther out into the infrared spectrum, you actually begin to image warmth and heat coming from an object. So you can see here the Hubble Space Telescope saw a little bit into ultraviolet light and a little bit into infrared, but it was mainly focused around visible light, which is the sort of light our eyes are using. The James Webb Space Telescope will start right at the red end, right a little bit redder than we can see, and go pretty far out into the infrared. We did have another space telescope that only ended its mission a couple years ago called Spitzer. That's what I worked on at Caltech and the Jet Propulsion Laboratory. And Spitzer was also an entirely infrared telescope, but nowhere near as large as Webb. Spitzer's telescope was about 1 meter across, so about 3 feet across, as opposed to 6.5 meters with Webb. So Webb is going to be, it really will be like opening a new eye on the universe. We've never seen the sky in this particular type of light. So it's going to be one of those discovery missions in the sense that pretty much anywhere you point this thing, you're going to see something you haven't before. Because we've never opened an eye on the universe just like this one. And the reason we're launching it into space is that infrared light is very efficiently absorbed by our atmosphere. I mean, think about it. Our atmosphere is warm. So the atmosphere itself is glowing. It's very hard to take infrared images and get infrared data when you're actually looking through warm gas on our atmosphere. So this is one of the telescopes that we absolutely have to launch into space. There's no other way to see this light. And we have never seen the universe with this particular detail, power, and wavelength. So everything's new. And if anybody's worried about not seeing images because this light is invisible to us, this is actually what I think is a very pretty image from the Spitzer Space Telescope. We got pretty good at NASA at assigning different colors to different wavelengths and different energies of this invisible light, infrared. And we're looking at a beautiful star formation region here. There are young star clusters like over here that are kind of blowing bubbles in the gas surrounding them. And it's a very different view of the universe because with a Spitzer image like this, the cold gas itself, gas that isn't glowing in visible light, gives off heat. And so the universe becomes much more full of stuff. everything that has pretty much any temperature at all. And I don't mean just hot things. Like, I mean, you and I think, are actually, pretty warm. We'll be able to see objects that have temperatures that are only, 10 degrees above absolute zero. So, I mean, in some cases, we're talking things that are very cold to us as humans, but they're giving off some heat. And so a telescope like this can still image them. So you will see beautiful images. I don't know exactly which colors we'll put on which different wavelengths, but there will be some lovely things to see. So don't worry about that. We won't just show you a blank frame and say, hey, there's an image. We'll do our best to translate it. So I mentioned there are advantages to infrared light. And I think this one shows you one very, very clearly. These are actually both Hubble Space Telescope images. And as I mentioned, the Hubble Space Telescope saw a little bit into infrared light. And these are the famous pillars of creation. These are gas clouds that are giving birth to new stars. There are new stars forming right at the tips of these clouds. And the new stars in visible light are still embedded in the dust that they're actually forming out of. A star forms when a cloud of dust and hydrogen begins to collapse under the force of gravity. And these pillars, by the way, are billions, hundreds of billions of miles across. They're absolutely huge. They're much bigger than our solar system. In fact, our solar system probably formed out of one of these about 5 billion years ago. This image that you see over on the right-hand side is a real image. It's just that this was taken in infrared light. And all of those stars that you see, that you don't see in visible light, those are all there. They're real. But the light was blocked by the dust cloud. So it's
Michelle,
amazing.
Can you hear me?
Sorry? Yes, I can. Yeah.
We have this image. We were lucky enough to get one from NASA, and I would like to show it to you all after the program.
Yes, it's one of my favorite images from Hubble, and then you can see the infrared. I mean, I absolutely love this one. And the pillars of creation are just so damn cool. They're really amazing. I mean, you really can see, if you look over here on the infrared image, you can actually sort of see into the dust to the warm areas where the stars are forming at the tops of these pillars. It's really, really amazing.
Beautiful.
So infrared is not an advantage just so you can see cold stuff, but you can also see through dust that normally obscures things like big black holes in the center of galaxies or stars forming. So again, an entirely new view of the universe. By the way, this is also an image of the Eagle Nebula. I'm not sure if you can find those 3 pillars. I'll give you a hint. They're right here, right down here. Yeah, there they are. So that's actually from the Spitzer Space Telescope. And here you can kind of see that these 3 pillars are actually part of a much larger complex of star formation and dust. And in fact, there are some very bright young stars up here, and the winds, the heat and the winds of particles off these stars are actually blowing back the cloud and exposing these pillars that you see. So you get a much bigger, broader context of the universe when you look at things other than visible light. Okay, there's another reason that visible light, that infrared light is so important to us as astronomers. And one thing is something called the cosmic redshift. And to put it very, very simply, the entire universe is expanding. Every bit of space is expanding in every different direction. And if you have light traveling through an expanding universe where the space itself is expanding, the light actually gets stretched out with the expansion of the universe. When I was teaching, I would actually draw a wave, like a sine wave going up and down on a piece of elastic. And then I would stretch the elastic. The universe is expanding. And so the wavelength of light stretches. And that means that the light loses energy. To our eyes, it means that the color becomes more reddened. And that's why we call it a red shift. And the more expanding space light travels through, the more this becomes important. It gets shifted more and more red. And so for objects that are very far away, say 13 billion light years away from us, that light has traveled through so much expanding space that it's actually been shifted out of visible light entirely. And so you see here, this is actually, it shows you sort of what energy we think light would be coming from very, very young stars, maybe the first stars that ever formed in the universe. Those stars were probably very big and very hot, and their light was mainly given off in ultraviolet. Ultraviolet light's the kind that gives you a sunburn. It's a higher energy light than what we can see, a little higher energy than violet. But with the expansion of space, that light has been changed so that mainly it's either invisible or infrared light. And it's lost energy as the universe has stretched it apart. So that's a really interesting effect of infrared light. You can actually see farther away. you can see objects that are so distant, their light has been stretched out by the expansion of space itself and are no longer visible in visible light. Okay, now something that I think is really cool about the James Webb Space Telescope is to make something that actually works well in infrared light. We've coated the telescopes with gold.
Those are your arms.
Okay, that sounds that sounds pretty expensive. It sounds pretty dramatic too. I've got a little short video that tells you a bit about why we chose gold, and you also get to see some great shots of the James Webb. It's late, and I'm jet lagged. I'm sorry about that. The James Webb Space Telescope. I don't know what I've been saying, but the James Webb Space Telescope. Here, I'll show you this little video about why the mirrors are coated in gold.
There's a lot of hustle and bustle because the integration is in full process.
Ooh.
Just look at NASA's James Webb Space Telescope. Its gold mirrors are definitely its most stunning feature. And yeah, that's real gold. Humans have a long history of searching for gold and using it in their most prized possessions. These mirrors weren't gilded to make them pretty. There isn't even all that much gold. About 5 men's wedding rings worth over the 18 mirrors. So I wanted to see for myself, why does it make sense to use a microscopic layer of gold on these mirrors? So our everyday mirrors tend to use silver or aluminum as the reflective material. One of the major differences between our earthly mirrors and these fancy optical mirrors is the position of the reflective material. Look at the side of this small mirror. It has the glass in the front and the metal coating behind it. That glass actually traps a tiny amount of light and creates what we call a ghosting effect. So the clearest reflection that we can actually have has the metal coating on the front. Dentists and hygienists also use front surface mirrors to get an accurate look at your teeth. The position of the reflective coating might make a sharp observation, but the kind of metal also matters too. There are a couple of reflective materials that really excel at reflecting infrared light, which is how Webb will observe. Aluminum reflects 85% of that wavelength of light, silver up to 95%, and gold up to 99% of all the infrared light that it encounters. But gold is special, and I can show you using the things that I typically wear. This one is gold, and this one is made out of silver. And in the presence of the right chemicals, these two materials react differently. I think actually it's a little easier to show kind of all of this with this spoon. My mom surprised me by pulling out this whole tub of silver. Not tub, it came out of a box. So I'm able to demonstrate sort of on a bigger surface here how silver can react differently using an egg. Smush that in. Get nothing. Get nothing. So what we have is a really fast reaction between the sulfur in the egg and the silver, and it creates a new thin layer on the spoon of silver sulfide. Silver might be great at reflecting infrared light, but it tarnishes so easily. Not only does gold reflect more infrared light, but it is also one of the most unreactive metals. It is too durable to oxidize and decay in space, and it is certainly Webb's best chance at seeing the cosmos.
Yeah.
Right. So the reason the mirrors are gold, and as we said before, it's a tiny little bit of gold. The coating is actually only a couple atoms thick. And so over that giant mirror, as she said, it takes only about 5 gold wedding rings to actually fill in all of that space. But it's very, very good at reflecting infrared light, and also it stands up very well to, over time, not reacting with anything and staying very clear. So we've got the mirrors, and then another thing that will be helping with the infrared is a huge heat shield. And I'll show you some videos of the heat shield unfolding. But the heat shield itself, there are 5 different layers. And each of these layers is about the size of a tennis court. It's very, very large. The hot side is going to be facing the sun at all times and keeping the telescope itself constantly in shadow. And of course, in space, there's no air to actually move the heat around. And so the idea is that the cold side will stay very, very cold, and it should never see the
This
sun.
is a
If it ever
heat
sees the sun,
shield.
that's a
Pass
problem.
this
Yeah.
down this side. This is a heat
Sorry?
shield from NASA. Pass it down and let everybody see it.
Ah, right.
She didn't know
Yes.
what she was passing around some
Heat blankets.
some heat blanket material just to
Heat blanket.
get a sense.
Yeah,
of
that's right. So indeed, you know, these heat shields are made out of heat blanket type material, very, very thin bits of it. So because the hot side will always be pointed towards the Earth and the sun, that's where we put all of our communications. And so that's where there'll be the different dishes that will download the images and upload commands. That's where we'll have a small solar panel to generate electricity, and also where we have our computers so they don't freeze really cold in the coldness of space. And then on the cool side, you have all of the telescope itself, all of the instruments, and that should get down to minus 388 degrees below 0 Fahrenheit. And the hope is to stay there. And one of the reasons it's going to take us a little while to get this telescope up and running, you're probably not going to see the first images until, I would think, about April or May, is we need to wait for the telescope to passively cool itself in the cold of space. And that will take some time. And then we will, once everything is cold, only then can we focus the mirrors and actually begin to open up our instruments and start testing them. So sort of the last thing about dealing with heat is the idea about the Webb's orbit, like I said, was not just chosen randomly. Going out to L2, 1 million miles away, so that's 4 times farther away than the moon, actually gives us a very cold area, away from the heat of the Earth and the moon. And also, the Hubble Space Telescope orbits the Earth. And so the Hubble Space Telescope, actually, it can only look at the sky for certain amounts of time. It can aim itself around, but some of the time the Earth will get in the way. And away from the Earth, we're not orbiting the Earth, we'll be able to look at the sky pretty much all the time. So there's a lot of advantages. And by the way, it won't stay completely still at this point, called L2, the second Lagrange point. It'll actually orbit around that point where the sun's gravity and the Earth's gravity line up and actually create a stable point. So it'll actually kind of slowly spin around that point once every 168 days. So that's the orbit. It'll orbit the sun itself beyond the moon, stuck in there between the Earth and the sun's and the moon's gravity, all kind of right in there. Okay, now as I mentioned, we also have this huge heat shield, and the heat shield actually works very simply. There are 5 different layers, and each one cools things down a little bit more. So you get light from the sun coming in that'll hit our heat shield, and the heat generated will actually bounce off its reflective coatings on both sides. So heat is infrared light; it's a type of light, and as you get closer and closer into the telescope, there's less and less heat to actually bounce away and reflect. And so by the time you actually get on top of these 5 layers, very little heat will actually get through to the cold side of the telescope. So we've got our heat shield, we've got our gold-coated mirrors, we've got our distant orbit, so we're ready to go to observe the universe in infrared light. And how are we going to do it? We've got some really amazing cameras. These are absolutely state-of-the-art instruments. Things like these, I mean, they're always the most advanced thing that's ever been flown in space, and certainly James Webb is no exception to that. There are cameras. There's near cam for near infrared cam. There's also a mid infrared camera, and then there are spectrographs, the mid infrared spectrograph and the near spec as well, that will actually break the light into rainbows. And that's just like Tish was showing you when she had that candle light maker, and you were looking at it through those gratings, and you could see all of the different colors that are components of that light. Today, when we were rehearsing, actually, to do the briefings for the James Webb Space Telescope launch, one person said it in a way that I really liked it. That I think John Mather, who's the head scientist and Nobel Prize winner, said, "Hey, a picture is worth 1,000 words. We can't wait until we have images." And then somebody came on afterwards and said, "Yeah, but a spectrum is worth 1,000 pictures." And when you actually spread the light out into a rainbow, you can tell what something is made of. You can tell how hot it is. You can tell how fast it's spinning. In the case of distant galaxies, you can tell roughly how far away it is. Very, very important information is actually contained in that rainbow of light called the spectrum. Another thing it's going to have is a coronagraph. A coronagraph actually blocks starlight using basically a tiny little metal disc. And the idea about blocking starlight out with a little metal disc is then you can see warm material around it. The heat and the light from the star won't just burn out your detectors, and you might even be able to see planets themselves, the heat from the planets, if you block out the light from the central star. Because in infrared, stars are still, millions or billions of times brighter than planets. Stars are very warm. But if you block out that heat light, you might be able to actually see the light coming directly from the planets themselves. And so that's called a coronagraph. And that's something that we'll be using too. So those are the specialized cameras and instruments on James Webb. So as I mentioned, we've got a bunch of neat things. We've got our cameras, we've got our spectrographs, and we've got coronagraphs. There are some slightly more technical things that I think are just wonders about this telescope. And I'm going to talk to you about the microshutter array and also the idea that we can take spectrum of objects in many different wavelengths at once, called integrated field units. But basically you can take a spectrum or a rainbow of a galaxy, but not just take it in one wavelength, in one range, but many, many different ranges of the spectrum at once. So we've got a really interesting sort of very diverse strategy about the way we look at the universe. Okay, these microshutters are again, first time these have ever been flown. You'll notice you're seeing some little, almost look like kind of little glass plates, and there seem to be bits that are missing or bits that are dark compared to the rest. There's a bunch of them over here. So these are actually tiny little things. The actual size of these arrays, each of these arrays is about the size of a postage stamp. And if I get this right, I think each array has about 62,000 tiny little shutters in it. So each one of these is small. Each one of these 4 components you see here is about the size of a postage stamp. And each one of these has 60,000 tiny little shutters. Yep, there we go. That can actually open and close. So I'm going to tell you about these microshutters because these are amazing. And they're going to allow the telescope to observe many different things at once. And so, everything about this telescope is just optimized to be as efficient as possible. So here we mentioned, so each of the quadrants is about the size of a postage stamp. Each of the quadrants has 62,000 tiny little shutters, little windows that can actually flip open and close. So in total, you've got 248,000 tiny little windows that can open and shut in this very, very little small array that the light will be focused through. So, why would we do that? why would we have tiny little windows to which to take our images and our spectra through? Well, what happens, I should probably say, the way it works is that they're controlled magnetically. There are very, very sensitive wires that actually magnetically flip each of these little things open and closed individually. So all of these microscopic, tiny little windows, little shutters, will open and close because of magnetic signals. And then what happens is that the light actually, if it's aimed through one of these little tiny shutters, it'll go right into the instruments. But the shutters actually can break apart different objects on the sky, so we can look at many things at once. And I think that's my next slide. Yeah. So what happens is, let's say we want to take spectra. We want to know everything we can possibly find out about all of these distant galaxies. And this is all in the frame of view that Webb will be looking at. We can open and close these little shutters so that only the galaxies we're interested in, the light gets into the detectors. And we can simultaneously take spectra of each of these little objects where the light is going down a shutter. Then you move to another part of the sky where the galaxies are in a completely different place, and we can do the same thing. We can open and shut these tiny little things individually and take spectra, get all kinds of information only about the things that we want to get. So it's going to have the ability to actually view many, many galaxies at once, get all the spectra at once, and we're going to be finding out incredible things about the sky in this very, very efficient way. All right, now, one of the things that I'm really looking forward to is the Webb Telescope, for the first time, should have the capability with these little microshutters and the sensitivity it has to actually be able to tell what the atmospheres of planets around other stars are made of. We should actually be able to get spectra from the atmospheres of planets themselves and tell if it has things that are Earth-like, or maybe they'll be more like a planet Venus, or maybe we'll find out that they're planets all of lava. But if you take the Earth, these are actually supposed to represent the Earth today and the early Earth as it was billions of years ago. The Earth today that we know has a lot of oxygen and methane, carbon dioxide, water vapor. Of course, our atmosphere is actually mostly nitrogen, and then things like ozone. And if you actually could look at the Earth when it was very young, say you look at the Earth about 4 billion years ago, you would have seen a lot less oxygen. Oxygen was released by plants over time, so you'd see more methane, nitrogen, carbon dioxide, and water vapor. So we're going to see sort of different signatures depending on the ages of planets. We're going to watch young planets forming. We're going to see, sort of if there's any planets out there that have Earth-like atmospheres. And I think it would be really amazing. The gases you have here in our atmosphere, oxygen, water vapor, methane, and carbon dioxide, having all of these present in an atmosphere at once is difficult to do without life. And so we may, in a few years, be able to look up at the sky on an observatory night here at Kopernik, point at a star, and say that star has a planet that has an atmosphere very much like Earth. We probably will not be able to tell you 100% that there's life there yet, but we'll be able to say, hey, we really do think it's possible it's a very good environment for life up there. This is actually just, for you science people, this was actually a simulation of what James Webb will be able to see in the spectra, where people are figuring out, what chemical signals. So if you think about the entire rainbow of light, all the different colors of the rainbow, what scientists read is that these sort of up and down lines tell you how much light. A lot of light is coming here, which corresponds to a signal from carbon dioxide, and also another signal over here. Here you have ozone. So we're actually busy simulating sort of what types of spectrum and what the light would look like, given different temperatures of atmospheres, density of atmospheres, different composition of gases. So we're all ready to go to figure out what the atmospheres are like around the exoplanets in the sky. And kind of wrapping up a little bit, so the thing that I think I am looking forward to most, certainly exoplanet atmospheres is one of the big ones, but I'm actually looking forward to actually seeing the first stars and galaxies form, get some idea about that. And I wanted to give you sort of a little bit of a time frame of the universe. So if we start here from where we're launching Webb, so this is what our universe is like today. The sun formed about 9 billion years after the Big Bang. So from our perspective, the sun formed roughly about 5 billion years ago. And so the Big Bang was a little more, 13.8 billion years ago. There was a very interesting thing that happened. We're going to talk about this a second. The first stars, we think, formed about 200 to 400 million years after the Big Bang. And there is actually a very difficult trick to seeing back to this time. I'll talk about it a little bit. So the Big Bang happened roughly 13.8 billion years ago. For quite a while after the Big Bang, there really was no starlight to see at all. And there was actually something else that makes it very difficult to look back to that time. And that's that the universe became neutral. It cooled down. And I'll explain what this means. It cooled down after the Big Bang. And what happened was that it cooled down so much that normal atoms were allowed to form. Atoms where there's a nucleus in the middle and electrons going around the nucleus. These are the atoms that we are familiar with most of the time in our life. Most of our atoms at this particular temperature and density have nuclei and electrons going around them. But in space today, almost all of the gas between the stars outside in the universe is what we call ionized. Ionized means it's been heated to such a high temperature that the electrons fly off. The electrons get so much energy, they fly off the atom. And so that's called an ionized atom. So for quite a while, the Big Bang cooled down, and for quite a while, the universe was cool enough that you had atoms in space that had electrons. And the reason this is important is that atoms that have electrons are very good at absorbing light. If you shine light at regular atoms with electrons around them, the atom will absorb the light, and the electrons will jump up and down in different orbits, but they'll stay around the atom. And so neutral atoms actually absorb light. When atoms are ionized and there's no electrons to absorb the light and jump around, light just flies right on through. So for quite a while after the Big Bang, the gas between the stars, the gas between the galaxies, was actually opaque. It absorbed light really well. And then when the first stars turned on and the first galaxies formed, there was enough energy, enough violent energy going out into space from these exploding stars, from hot areas around black holes, that the universe became ionized again and we could see through it. But there's this time here, the dark ages and reionization, that we've never been able to see back into. And yes, I mean, reionization, when the universe had neutral atoms, it absorbed infrared light too. So infrared light doesn't really get you around this. But we're hoping that as the first galaxies form, there'll be some bubbles of hot gas around these first galaxies that will actually let us look through to that time. And so we really are trying to look back to the time when the first stars and galaxies formed. And I think that we're going to find out some amazing things. One of the big mysteries right now in astronomy is that when we look back to this time, as far as we can see, there are giant black holes that are millions or billions of times the mass of our sun. And we have no idea how black holes that big could possibly form that quickly. So basically, the first stars start to form, and very soon after, you have black holes that are millions of times the mass of the sun. And as far as we understand black holes, they form when stars die. And one black hole can swallow another black hole, and so you can build up a pretty big black hole. But we don't know how you get a black hole that's a billion times the mass of the sun when the universe was only a couple 100 million years old. So that's one of the big mysteries we're trying to figure out, is how do you get these big black holes so early in the universe? So as I mentioned, we're here at the present day. We look back in time to modern galaxies, and then there's this time that's very hard to see because the gas becomes more and more opaque. But we do think it's probably uneven. There are probably bubbles blown from exploding stars that we could probably see a little bit back into this area. And then we're into the dark ages, where the gas is so opaque we really can't see very much at all. The reason the first stars are going to be like really exciting to see is that we have no idea how they worked. You only have the elements that were present in the Big Bang to form stars. Everything that you see in this room, like the carbon that makes up my body, the gold in my ring, my teeth are made of calcium, the reason my blood is red is because there's iron in my blood. All of those elements are formed in exploding stars. There's no other way to make calcium. So the calcium in your teeth was formed when a giant star exploded and created that chemical element. That's amazing to think. The universe has no other way to make a calcium atom, no other way to make the carbon that actually makes up most of your body. So the first stars were they had none of these other elements. So the Big Bang created hydrogen and helium with a tiny, tiny, tiny little amount of lithium. That's it. Those were the only chemicals that existed in the universe when the first stars formed. The sun today, although it's still mostly hydrogen and helium, it's 2% heavier elements like oxygen, carbon, iron, and all of that. And the reason the sun has those elements in it is because it formed from the debris of other exploded stars before it. So we know the sun was not a first-generation star. It has all this other chemistry to it. And that chemistry affects the way the sun works. So we don't really understand how a star would work if there was none of those other elements, just hydrogen and helium, basically. So one of the things we hypothesize is that they might have been huge. They might have been hundreds or thousands of times the mass of the sun. And they might have actually not lived very long at all. The gravity brought all of this material together that then immediately exploded. And so I kind of call this the party at the beginning of the universe. This is kind of an artist's conception of giant stars exploding and sending off big clouds of gas. This actually might be what the universe looked like. There was no dust. It's just gas and all this hot material coming out of the very first stars. We don't know what these first stars were like. They might have been dominated even by dark matter, that mysterious matter that we don't understand yet. It could be that helped form the cores of these stars. So we have a really wonderful time trying to figure out how, what that early part of the universe would be like. Okay, so I think, yep, okay. So what I want to do is I want to quickly just end on some videos. This one's just a little bit long. It's about 8 minutes long, but I think it's worth it. And it's going to talk you through everything that has to happen to get this telescope to work, plus some of the objects we're hoping to see. And if you're not a bit scared by the end of this video, then I don't think you're human. So here we go.
This is a science mission on par with the Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. It all comes down to this. Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1 million miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold like origami to fit inside the rocket fairing. And this brings us to our most challenging part of this mission, unfolding it in space. Tish, say, got it. Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket. For the next 8 minutes, the explosion from that rocket is following you in outer space. Vibrating, shaking. Everything that goes in outer space has to live through this environment and work once it gets there without having someone come to fix it.
Two weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail-biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks. This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from recent engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our Huygens antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1 million miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield panel, then raise Webb's primary mirror and instruments away from the sunshield. Solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, folded segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers, approximately 8,900 square feet, almost the size of 3 tennis courts, of very thin Kapton material, about 1 to 2 thousandths of an inch thick. Making them go where we want them to go in zero-G is extremely challenging.
The sunshield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sunshield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this powerful restraints that protect the sun shield during launch. They roll out of the way, but not all the way until we are ready to deploy a side. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sun shield release mechanisms need to fire on cue. 107. They freed the 5 sun shield layers, allowing them to extend as the mid-booms deploy.
With the sun shield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
With all the instruments cooled, we'll control motors behind each of Webb's 18 mirror segments, the secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
This is
Oh Lord. So like I said, if you're not scared, don't talk to me for a few months. This is what I'm going to be worrying about for the next. Oh, I don't know. I might be able to breathe sometime in like March, I think. But I mean, you know, you saw how many things have to work, and they all have to work, and it blows my mind. Of course, we've tested. Of course, we have our best engineers working on it. This is risky. It is absolutely risky. And when people say things like, you know, NASA's $10 billion telescope and all that, the thing you have to remember is we've been working on this, you know, in one way or another for about 25 years. And over that time, it's employed thousands of people around the world, tens of thousands around the world. You know, there have been many companies that have contributed. You know, it's been a 25-year project. We didn't just like pack $10 billion and launch it into space. The $10 billion is what it took to develop these things, to build them, to employ everybody for, in some cases, people's careers. And so, you know, I mean, while, you know, I am, you know, absolutely touch wood and everything sure that this is going to work. If for some reason it doesn't, we have learned so much from making this telescope that you know, we're ready to take that risk. And I thought I'd just give you just before I end, just a little couple short videos of watching it get deployed. So here we are packing it up. It's going to be put on a ship at this point, and so it's already arrived. But here we're actually loading it from California, north of Grumman. A lot of components of the observatory were built at Goddard. I was actually watching them build this on my lunch break. My husband actually was the lead on the portable clean room and protector that actually this is contained in. So there's a lot of him in there as well. But I just wanted to show you sort of packing it up and getting it out. we did indeed put it on that ship, and the exact time was classified because this has been identified as a terrorism target, but it did arrive safely, and here it is on the other side. Right. So this telescope is something that I've been I've been eating and sleeping with it for 10 years. My husband was a major engineer on this. I know he was losing sleep. I know he did his best to do this. So this is family. And like I said, the thing is that anything we see is going to be new. We've never looked at the universe this way before. We're going to see farther than we ever have before. We're going to see exoplanets in ways we never have had before. It's going to be an international observatory. Once we accomplish some of our major first observations, it's open to anybody with a PhD to apply for time on it. So there'll be a once-a-year call for everybody to write in from around the world and say what they want to use the telescope for. And then there'll be committees of scientists all around the world that will rank the proposals. This is an international observatory to be used by all of the scientific community. And the data is publicly available, I think, just a few months after we take it. So everything we take is available and completely publicly accessible and will be archived for people to use for decades to come. So I am really looking forward to this. Some of you know, my husband died about a year ago. He will not be able to see the Webb Telescope launch. He probably would have been one of the engineers to accompany it actually, because he was actually working on that. But this is a bit of him in space and a bit of his legacy coming up, and I'm really looking forward to seeing that happen. So I will stop, and if we have time for a few questions, that's fine. And I also want to get you guys out to that beautiful night. So thanks.
Of course.
Well, we actually do have at least one that came in over the YouTube chat, so we'll start there.
Where are my heat blankets?
And this is from Only in Antarctica. That's though he said he's not in Antarctica, so I understand.
I'll be in Antarctica in January.
Oh, really?
I'm really looking forward to it. My first trip, hopefully one of many.
That's the warm season down there in January, right?
That's right.
Yeah. So anyway, the question is, can the James Webb see through our Milky Way galaxy to see more of what's beyond?
Yes, absolutely. So that's one of the main goals of seeing through dust. So the Milky Way galaxy that we are living inside of, we're basically living inside a smoke ring. And the galaxy actually blocks out a lot of light coming from space. So most of the very distant galaxies we see, if you can think of the Milky Way galaxy being sort of the shape of a frisbee, a disk. So we're not in the center. We're about 2/3 of the way out along one of the edges. But that disk is full of dust, and we're inside that. So if we look sort of up above the disk, that's where we see sort of other galaxies. But looking through the disk of the Milky Way is very hard. And so absolutely. So looking through the disk of the Milky Way, not just at distant galaxies, but also into the center of our galaxy, which has things like a giant black hole. So there are lots and lots of things to discover looking through the dust of the Milky Way galaxy. It's a major goal of James Webb.
Did you see this?
All right. Any questions here? Oh, we got one right here.
How did you name the planets?
How do we name the planets? Like all of the different planets around other stars? Unfortunately, all they have are numbers. We really don't have. I mean, so right now, and this changes every day. In fact, if you go to a website, exoplanets.nasa.gov, you'll see a counter that changes every day. Right now we know of about 4,000, it's getting close to 5,000 planets around all the stars in the sky. So if you look up at the stars tonight, most of those stars have planets and solar systems around them that we've discovered in the last 20 years. We're also following up on another 8,000 candidates where we think we might have seen a planet, but we need more observations to confirm it. So that's how many planets we've found just in the last 20 years. And that's going to keep increasing all the time. At NASA, we estimate now we'll find about 1,000 planets a year around other stars in our galaxy. And we estimate that our galaxy alone probably has many hundreds of billions of planets. And because there are so many of them, really all they have are catalog numbers. They don't really have anything particularly interesting as far as names. Hopefully someday there'll be some planets well known enough. Maybe after James Webb finds they have Earth-like atmospheres, we'll actually start to name some of these. By the way, things in space are named according to different rules. If you discover a comet, the comet is named after you. So that's automatic. If you discover a comet, the comet gets your last name. If you discover an asteroid, you get to name it. You get to decide what to call it. And so a lot of people who've discovered asteroids have named them after their favorite rock stars, like Frank Zappa and the Beatles and all of that. Different people in history. But everything as far as stars and planets, that's named by an international committee. So you don't get to just discover a planet and then call it, Fred. I mean, that'd be a lot of fun, but you don't. It's all named by your international committee. And by the way, I hate to say, if any of you ever bought, name a star, that actually no scientist ever gets that information. That's kind of a scam.
All right, we have another question from the YouTube. This is for Joe asks, can you estimate what the visual magnitude will be as seen from Earth?
Oh, and so that's something where that's dependent on the wavelength and things like that. I don't know exactly. I will be straight up honest about that. I am a manager at NASA and an astronomer, but I'm not an absolute expert on the instruments. But I bet I could find that out. I know, for example, to give you a sense of how sensitive this telescope is, if you had a bumblebee on the moon. And let's just assume for a minute it won't freeze and die instantly. If you had a bumblebee on the moon, the cameras would actually be able to resolve it. You could actually see the bumblebee on the moon, and it would be able to detect the heat of the bumblebee. So the infrared sensors are so sensitive that from Earth you could actually image and detect the heat of a tiny little bumblebee on the moon. And I know that's not a number, but you may be able to find out in the website. There are lots of NASA websites on the specifications of Webb, and if it's really important, I might be able to find it out.
Excellent. Any other questions? Yeah, another one over here. So, Elsa, why don't you come over here so she can see you?
Hi there.
What will happen to the rocket ship after it drops off the telescope?
Yeah, the rocket ship will some components will fall back to the Earth, and I'm not sure if anything actually just kind of remains going out into space. I think it pretty much all falls back. The rocket ship has solid rocket boosters that actually get it first up off the Earth, and those will fall back to Earth. And then there is another large tank of rocket fuel, and that largely falls back and burns up in the atmosphere. So there's really not much we can recover from the rocket. That's used for the launch, and that's it.
All right, any other questions? In the back, so give me a second.
Hello, I wanted to know why the mirrors on the James Webb Telescope are hexagons.
That shape fits together very well, and that's been actually used very successfully in large telescopes here on the ground. I don't know if any of you that have been out to Hawaii, but the largest optical telescope right now is the Keck Observatory in Hawaii, and that also has large hexagonal segments. And the hexagons can lock in very, very close to each other, but you can also move them independently. The shape works very well. And the next generation of giant telescopes, and these are ones on the ground, by the way. So we're getting very, very good at visible light telescopes on the ground, at actually making them very clear. So NASA doesn't really have any plans to launch another telescope like Hubble, where it mainly sees invisible light, because our ground-based telescopes are getting better and better all the time. And the ones that we're building right now have mirrors that are they're on the order of about 30 meters across. So that's about 100 feet across. I've had the chance to visit 2 of them being built in Chile. They're not done yet, but I visited the sites of the ELT, which unfortunately does stand for Extremely Large Telescope. That's really true. And there's another one called the Giant Magellan Telescope, also in Chile at Las Campanas. I've been to both of those to see them being built. And there'll be another one built either on Hawaii or perhaps the Canary Islands called the 30-meter telescope. So those are coming up soon. And the hexagonal mirror technology has proven really well. It fits tight. You can actually tile a very nice space with no gaps in between, and yet you can move them very, very easily independently. So it's worked well in our telescope technology on the ground. You're trying to basically make the curvature of each segment, although each segment is flat, you're trying to line them up into a curved mirror, just segment by segment by segment, so that it functions mostly as a curved giant mirror. And then the segments just allow you to make a bigger mirror than you could possibly cast out of a single piece of glass. So I mean, they've allowed us to go from. I mean, think about it. So you've got Mount Palomar, which is the 200-inch telescope. That's a single block of glass. But then you go to the Keck Observatory. The Keck Observatory is 10 meters or 30 feet across, and it's all in these hexagonal segments. So it allows you to build a bigger telescope than you could possibly make as a single block.
I'd actually. To loop back to the magnitude question, actually Joe was I think clarifying his question. He meant how bright will it look? I'm wondering, will we actually be able to visually see Webb as a pinpoint sky?
Oh no, we won't be able to actually see it from Earth. Is somebody thinking about doing some astrophotography? Well, so I mean that's a good question. I mean, if I don't know if it will reflect any amount of light that's possible to see. I honestly don't know, because it's although it's a big telescope, it's a tiny little thing to see a million miles away. So my guess is no, that you won't be able to actually resolve it in the sky.
Right. All right. Very good. Any other questions here in house? Oh, another one. Give me a second.
And then we need to get you guys out to that beautiful night. So.
Now, since it's orbiting the sun farther away from the Earth, it should go slower than the Earth and therefore not orbit with it. But by orbiting around the Lagrange point, will that keep it in sync with the Earth's orbit?
Yeah, that's right. So the Lagrange point is a fixed point in space, and it's basically a million miles away straight through Earth at kind of a right angle to the sun. And there's all kinds of information online if you want to know about Lagrange points and kind of how they work. So in this case, the Lagrange point travels with the Earth at the same rate as the Earth. So by orbiting around the Lagrange point, it stays fixed compared to the Earth in space as the Earth goes around the sun. So yes, it'll be orbiting with the same period as the Earth, stuck into this sort of balance zone between the gravities. Yep.
All right. Well, Dr. Fowler, we can't thank you enough for your time and expertise and enthusiasm about this topic, and Tish.
Everybody keep your fingers crossed for like the next 4 months.
So the current launch date with no slip is what? December
18th.
18th.
Yeah.
Okay.
And so far we are working to that date. I mean, but once we get this close, it becomes harder and harder to make any significant delays. The rocket's going to be ready to go. Everything is integrated and ready to go. It's in, so I mean, it's, I got my fingers crossed, and I haven't heard of any significant delays so far in getting it put on the rocket. So join us for December 18th, and actually just this coming week. So a month before. We call this T-minus 30 days, a month before the launch. We're having a major briefing at NASA. I will be hosting that briefing and every other major briefing for the James Webb Space Telescope through until spring. Okay. So we're all rehearsing for that briefing right now, and I'll be the main host on behalf of NASA for all of the media coverage for the Webb Telescope.
Outstanding.
Right.
Is it a daytime launch or is it a night launch?
Oh, I should do this. I need to find this. I think it's a daytime launch. Okay. I think it is, but I can find out. And you can probably find out on the website too. Okay. But I think it is. Yeah.
I think it's worth us. We've live streamed and had sort of a launch party on our YouTube channel for Perseverance, for the Demo 2 Crew Dragon, because Doug Hurley grew up about 5 miles from here, and so I think this is definitely a live stream worthy, and so we'll look forward to that. So
Yeah, so yeah, the launch, and like you said, I mean, some of these things happen just a few hours after launch,
mhm.
and then this thing has to keep unfolding, for the next couple of weeks, and then we have to make sure everything gets down to temperature before we focus and turn the instruments on. So yeah, that's going to be some interesting winter and spring for us. Yeah.
Okay.
Make it happen. All right. Well, thank you so much again.
Thanks for having me. Thank you. Nice to be here.
Have a great weekend. Actually, I'm actually stopping in your neighborhood. We have a lunar sample up here right now, and I have to return it on. I have to return it on Monday.
Come by for a cup of tea or something. I mean,
All right, I'll email you.
You need a place to stay. I've got a guest room. Yeah.
Actually, we'll talk.
Wait,
All right.
right here, don't take it.
So, thanks again, and
Bye.
so long.